Section 2.5 describes how atomic masses are calculated. While the textbook only offers one learning goal, we've identified several more specific learning outcomes to keep in mind as you study the material. If you can accomplish the learning outcomes without your notes, you're more likely to enjoy the greater chances of success on the exam. Let's begin. Because atomic masses are so small, they are measured on a relative scale with one isotope assigned a value and all other measured relative to that isotope. Initially, the standard was set as oxygen, with the naturally occurring mixture of oxygen isotopes assigned a value of exactly 16 atomic mass units, U, sometimes abbreviated AMU. In 1961, the mass of carbon-12 was designated as the new standard, with carbon-12 atoms assigned a mass of exactly 12U. For reference, atoms will have masses between 1 and 250 atomic mass units. The atomic masses we see on the periodic table are weighted averages of the actual masses of naturally occurring isotopes of an element. For example, if we consider the element carbon, we see that the three most common isotopes are carbon-12, carbon-13, and carbon-14. If we were to add these three masses together and divide by 3, we'd get an unweighted average of 13 atomic mass units, which is incorrect because it implies we'd come across this mass of carbon in nature far more often than we actually do. Instead, we take the weighted average by considering that carbon-12 has an abundance of 98.9%, carbon-13 is much less abundant at 1.1%, and carbon-14 is the least abundant, composing less than 0.1% of all carbon found on Earth. Converting the abundance percentage into a decimal, then multiplying by the weight of that isotope, gets us the weighted average of carbon found on the periodic table, which is 12.011. Let's consider a more concrete example to demonstrate. Most of your college classes will use weighted grading, meaning that some assignments, such as exams, contribute more to your final grade than participation. Let's consider this example. In one class, exams are worth 50% of the overall grade, quizzes are worth 25% of the overall grade, homework is worth 20% of the overall grade, and class participation is worth 5% of the overall grade. A student has earned an average score of 80.2% on the exams, 77.3% on the quizzes, 87.8% on the homework assignments, and 100% on class participation. What is the student's overall grade in the course? If you're anything like me, you probably blanked out a little when you saw a wall of text with numbers in it. To break this problem down into manageable bits, I like to use graphic organizers and tables to sort the information before attempting the calculation. Let's do that here. I've already listed each of the components of the class in my table. We need to record how much they contribute to the overall grade, or their weight, the student's score on each component, and the points earned from multiplying the weight by the score. Exams are 50%, quizzes are 25%, homework is 20%, and participation is 5%. We'll record each of these as the decimal version of the number, so we record 0.50, 0.25, 0.20, and 0.05 for participation. These are the weights, and their total sums to 1. Next, we record the student scores, 80.2% on exams, 77.3% on quizzes, 87.8% on homework, and 100% on participation. We'll keep these values as whole numbers, dropping the percent signs. Next, we multiply each weight by the score earned to get the points earned out of a possible 100 points for the class overall. We see that the student has earned an 82% in the course. If you need a deeper review of this process, consider working through section 0.9 of the textbook for a refresher. We can apply this method of calculating weighted averages to atomic masses as well. The atomic mass is the sum of the fraction of the isotopes times the masses of each isotope. This is equivalent to multiplying grade weights by percentages on the previous problem. Let's work through an example. Calculate the atomic mass of copper, given that naturally occurring copper consists of 69.17% copper 63, which has an isotope mass of 62.9396 atomic mass units, and 30.83% copper 65, which has an isotope mass of 64.9278 atomic mass units. This problem only has two isotopes, so we can solve it without a graphic organizer. First, we convert the percentages to decimal numbers and multiply them by the masses. If you'd like to see another example worked, please see Figure 2.13 in the textbook where Tyler works out an isotope calculation for lithium. Atomic masses of naturally occurring isotopes are listed in the periodic table. Using this definition, then, means that artificial elements, which are all elements with Z greater than 92, do not have atomic masses. Instead, the mass number of the most stable isotope of each artificial element is given in parentheses, as you can see for all elements listed after uranium, element number 92. By the same definition of atomic mass, we see that artificial isotopes of naturally occurring elements do not contribute to the atomic mass. As always, I'll leave you with the parting thoughts of the authors.